Hello, everyone. Welcome to Talking Robotics. So this week, we invite Pozzi for our talk. Pozzi is a fixed-term assistant professor at University of Siena and affiliated researcher at the Italian Institute of Technology of Genova. She holds a Bachelor of Science degree in 2013, a Master of Science degree in 2015, and a PhD in 2019, all with honors from the University of Siena. In 2021, she was selected as an RSS pioneer and was invited as a speaker for the IFRR Global Robotics Colloquium on the future of robotic manipulation. Her research interests include robotic grasping, simulation of software robots, and haptic interfaces for human-robot collaboration. Since 2021, she has been associated editor of the IROS conference, and since 2023, she has been associated editor for the IEEE RAM magazine and IEEE RAL. Today's topic is mainly about the advent of soft robotics has greatly changed researchers' perspective on robotic manipulation. This presentation will outline ongoing research efforts on how to unlock new manipulation skills in soft rigid grippers, and will discuss the application of soft manipulation principles in human-robot interaction. And let's give the talk to Maria.
Okay, thank you very much for the introduction and for the invitation. So I will now share my slides. Okay, starting from the first one. All right, so I guess you can see the slides and you can also hear me, and so I will just start. Right. So again, thank you for inviting me. I'm Pozzi and I'm from University of Siena. These are mostly information that were already given in the introduction, but I just wanted to point out that these are the beautiful places where we are working. There is Siena City and then our department in Siena, which is the Department of Information Engineering and Mathematics. I did my bachelor, master's, and PhD with professors Pratichizzo and Malvezzi in the SISLab Robotics Systems Lab. Actually, the research that I will present today really is immersed in the context of the lab. In our lab, we are mainly expert in haptics, so whatever is related to the sense of touch, and robotic grasping and manipulation. And then we apply these two topics, these two lines of research to human-robot collaboration and wearable robotics, mainly in assistive applications. One thing that you can see in this slide is that basically every picture has a hand there's a hand in each picture of this slide. And well, there are human hands, robotic hands, as well as simulated hands. So our focus is really on the hand as an organ that allows us to interact with the external environment, both in terms of perception and action. Today, I will focus more on the, let's say, grasping part, okay? So, as I said in the title, soft robotic manipulation is really about embracing the physical interaction with the real world, because interaction is fundamental in every manipulation and grasping task, whether it is done with a rigid hand or with a soft hand. But while rigid robotic hands are typically controlled to perform a certain type of interaction, and so the interaction is controlled and minimized typically, because if you see a grasp performed by the rigid gripper, usually this is performed as a precision grasp with a few contact points, and typically the environment surrounding the objects that are manipulated is perceived as an obstacle of the task, okay? On the other hand, soft manipulation embraces interaction in the sense that interaction is not only fundamental to actually achieve the grasp, but also it's exploited to perform a robust grasp. Here you see some examples. We will go through them a little bit. So The design of soft hands basically bridges two main research lines that is the research line on robotic manipulation and grasping and soft robotics. And soft manipulation shares the same philosophy of soft robotics, according to which embedding compliant elements into the gripper structure allows to embody some intelligence directly in the hardware of the gripper. This means that, as a result, in principle, there should be a reduction of the requirement in terms of perception and control, so the requirements on the software side. However, still we are struggling and we need to research on how to actually design a certain robotic hand. How to design a clever hand, clever enough to perform a certain manipulation task. And this is a quote from a paper of 2020, but I think it still holds true because there have been some, new efforts in the research community, a lot of newer results, but still we need to continue in this line. So now I will briefly present you some results that we had related to the main question of how we can suitably exploit the hand environment interface in manipulation tasks. So given that we have a soft hand, how do we actually exploit it in manipulation tasks? So the initial works we focused on mainly were about exploiting environmental constraints with soft hands. This means that we take soft hands. Here you see two examples. Basically, one is a pneumatic hand, the RBO hand, and the other one is a tendon-driven hand, that is the soft hand from IIT and Pisa. And we tried to control these hands in order to grasp objects while exploiting the environment. In the first case, you see a surface-constrained grasp. In the second case, you see an edge grasp. In both cases, we employed a model-driven approach to align the hand to the object, and then we let the hand finish the grasp by enveloping the object. And this last part, the very last part of the task, when the hand really starts enveloping the object, is actually left to the hardware of the hand, which then envelops the object. Then, going ahead from this paradigm in which we have a soft hand against a rigid environment, we ask ourselves, okay, what if we still want to use rigid grippers? Can we make the interface between the hand and the environment still soft? And the answer is yes, but we need to make the environment soft. So we created a pneumatic pad that you see here in the video, above which we would place objects. Thanks to the fact that this pneumatic matrix is connected to pressure sensors, we could sense the object position as well as the contact between the rigid gripper and the environment. And then based on that, we perform the grasp. In this way, we sort of demonstrated that if you make the environment soft, you can also allow rigid grippers to exploit environmental constraints. As a further step, we ask ourselves whether actually we could embed a sort of constraint directly into the hand structure. And here you see a gripper that is called a soft scoop gripper, which has a sort of scoop structure attached to its palm. The scoop is actuated and is connected to the palm through a flexible hinge. And it's a sort of second actuated palm, which opposes two soft fingers. In these works, we had the first part of the planning of the robot motion based on optimization done in simulation for the pre-grasp pose, and then we let the hand finish the task, which means enveloping the grasp with the two fingers opposing to the scoop and enveloping the object. So going ahead in this direction of asking ourselves how to exploit the hand-environment interaction, I will now present a few more recent works in which we try to answer other research questions. In particular, we ask ourselves, okay, so we have seen that this sort of a scoop-like structure enables the exploitation of environmental constraints, and in particular, it allows to detach the object from the surface over which it's lying, or if we also tested cases in which the object was close to a wall, and then the scoop would go down and separate the object from the wall. So we ask ourselves, okay, suppose we want to automate the design of this particular part that is the scoop, and then possibly enable these kind of strategies that we showed, even in different hands. Well, we tried to do this, and the idea was to then attach an add-on, a scoop-like add-on, to a commercial robotic hand. And here you see an example of a task. I will show it again. The hand is trying to grasp something into a box. Here it doesn't have a scoop. Here it has a scoop. And as you can see here, the scoop slides along the box and then separates the object. And then it also opposes to the thumb of the hand to grasp the object. So just thanks to a simple, rigid surface attached to a soft hand, we enabled a strategy that was not possible before with this kind of hand. To give you a little bit more details, we created a data design pipeline for these embedded constraints. And the interesting thing is that we fed an optimization process not only with the hand model and the object models, which is something typical in grasp planning, optimization-based grasp planning, but we also embedded the information on the relative pose between the object and the environment. So the environment is part of the manipulation task. In our optimization process, we optimized both a classical grasp quality measure and also the alignment of the scoop with respect to the environment. And then we obtained the parameters, which means the length, width, the distance, and the orientation of the scoop on the hand palm of several different grippers, because we tested them with several different objects. Then we had to cluster these parameters in order to find the most representative grippers that then we would have prototyped. So this first part was conducted in simulation. Then we took the final scoop parameters and prototyped the scoops. Here you see, for example, the table with all the parameters that were chosen. And so we found 3 different scoops with respect to the original one for the scoop gripper and 4 different scoops for the PISA IIT soft hand. Then we trained a network to actually choose the best scoop depending on the object to be grasped. And here I will show you just the results with the PISA IIT soft hand. We tested several different objects, and we saw that with the scoop, we really enabled this new strategy that would be otherwise very difficult for the hand. I mean, grasping something that is constrained on one side is not easy. You should do it with 2 actions, for example. Okay. And so from these, we continued in our research, and the next question for us was, okay, so we show that exploiting environmental, not only us, I mean, the whole community of soft manipulation showed in several examples and with several different hands that exploiting the environment can lead to more robust grasps. So we ask ourselves, okay, first of all, can we use these kind of strategies even when handling objects that are rather fragile, like food items? And second, and most important, can we use this environmental constraint exploitation even when releasing objects? Well, inspired by a competition in RoboSoft that was about grasping food items, we designed this gripper that features two scoop structures attached to soft fingers. It has an onboard camera, and strangely enough, it has a tube that allows to separate the gripper part from the motors that then are attached to the robot and effector. This tube allows to enter narrow spaces, as it was required by the challenge, and in general it would be required in this kind of task. And the scoop would the gripper would use the scoops both during grasping. And here you see, are there questions? Okay. Here you see an example. And during grasping, the onboard camera is used to decide which kind of strategy to adopt, and then also to place the food, because thanks to the scoops, the food can be placed gently inside the container. Here I'll briefly show you the different strategies for picking that we implemented to show all the potentialities of the gripper with two scoops. And here the placing strategies. So we have from an easier strategy, that is the one applied with the plate, which is bigger than the gripper, then the strategy applied with the bowl, and then the strategy applied with the glass that is smaller, so it requires the gripper to flex. Again, even in this case, once the gripper is aligned with the container in the most suitable way, the rest is left to the interaction between the object, the gripper, and the environment. So here you see the results. We were quite successful, above all in releasing, but also in picking up several different objects. So the next question for us was, okay, we have seen that embracing interaction is very important in grasping, releasing objects, even with the special strategies like the one that I showed you with the scoop gripper. Can we also exploit this kind of interaction in human-robot collaboration? And we devised an handover strategy in which the human basically with the open palm brings an object to the robot, and the robot grasps it by sliding the fingers on the human hand. We ask ourselves whether this strategy would maintain, this kind of application would maintain the same properties that we have seen in autonomous grasping, and then we ask ourselves whether this strategy would be accepted by users. So to implement this strategy, we implemented a perception pipeline, starting from the estimation of the hand pose, and then going towards the extraction of the point cloud of the object. And then based on the point cloud, we computed the bounding box of the object, and then we performed the grasp. Again, here there is a certain intelligence, let's say, in the perception pipeline. Then once the hand goes down and closes on the object, it's the hand compliance that takes the job, that does the final part of the job. Here in this slide, in the video here, you saw an handover performed with our strategy, which we call the soft handover. We then compared this soft handover with the baseline, which basically is a position controlled strategy in which the hand goes down up to a certain height over the object and then grasps it. Okay, in terms of results, first of all, we checked the success rate of the two strategies with different objects. And we saw that for certain kinds of objects, the performance is quite similar, but with irregularly shaped objects and very small objects, the strategies are different. So the handover works better, if, for example, with articulated object like the. Then we tested whether the hypothesis that we were talking even before about, like, so do we get more robust grasps, even in the case in which we are interacting with the human hand? And the answer is yes, above all with small objects, again, because we tried to compute the grasp success, simulating some uncertainty in the positioning of the object, and we saw that for small object above all, the soft handover was much more successful than the baseline. For bigger objects, this discrepancy reduces because in the end, the fact that the hand touches the palm plays a very important role for small objects, whereas for bigger objects, this might not be important. Then we conducted a user study with 30 participants and 9 different objects of different sizes with both strategies. And what we wanted to see was whether, the user subjective experience with the system, as well as the possibility of using the system with many different users. What we saw by asking questions was that for small objects, again, the soft handover was perceived as more natural and reliable. It was easier for the users to interact with the system, whereas for medium-sized objects, there was not much difference between the baseline and the soft handover. And with bigger objects, there was some minimal discomfort perceived by the fact that the hand was pressing a little bit against the palm of the human hand when it encountered the object. So here are some results, and the interesting part here is that for smaller objects, which are those that are that also achieve a higher success rate with respect to the baseline, the system is not only perceived as more reliable, but also as more natural. So it's sort of aligns with our idea that if we have a small object on the hand, probably we would do something like this even when interacting with a human. So we have seen that from the initial results that we had in terms of hand environment interaction, we ask ourselves other questions, and we got some results. But so I think the fact that this field, the field of soft manipulation, continues to pose challenges and make us ask questions about it, indeed shows that the future of manipulation is soft, probably soft rigid, because as you have seen, the addition of some rigid parts suitably designed and put in the structure of the gripper actually help the gripper. But I think, and what is also shown in the what we can see from the literature, we are quite now good at designing soft grippers. There are a lot of prototypes that have been are being produced in terms of different materials, different actuation principles. And as you can see, in the last 10 years, there's been a huge growth in this field. But still, we need to understand well how to then exploit those capabilities in a clever way, meaning by having planners and perception systems that are a little bit simpler than for rigid grippers, right? So that would be the ideal result of soft manipulation and soft robotics in general. And one way to go, and what we are now trying to understand, is the relationship between learning paradigms, learning algorithms with the hardware. So, for example, if you look at the recent review on deep learning approaches in grasping, the authors underline that there is a lack of soft grippers used in combination with learning algorithms. And so we are now trying to ask ourselves, how does the hand design influence robot learning? Can we exploit the intelligence in the hand to sort of simplify robot learning? And so just to conclude and give you a hint on also other ongoing works, indeed, we saw how embracing the physical interaction with the real world enhances robot grasping, as well as human-robot collaboration in some cases. I just wanted to acknowledge the work of several colleagues, which are allowed to bring ideas into real implementations. And the part that is missing here, as I'm saying here in the title, embracing the physical interaction with the real world is the first step towards creating systems that can actually help people in assistive scenarios, which are those that, as I said at the beginning, we are tackling in our lab. And what is missing, the second step, is to create a way to let the human and the robot communicate in an explicit way, not only through contact. So in our lab, we are also developing wearable interfaces that allow to create a loop between the human and the robot. The human can send commands to the robot while interacting with it and receive feedback, awareness, alerts from the robot, for example, through haptic signals. So the missing part, which I didn't talk about much today, is the human-robot communication, so which is an interaction, but it's a non-physical interaction. And this missing part will allow us, and is allowing us, to tackle complex scenarios in which the user is connected to a robot and performs complex manipulation tasks, while the robot has grippers and the capabilities to actually interact with the real world. So with this, I would conclude my talk. Thank you for your attention, and thanks to all my collaborators and the projects for the huge work. Thank you.
Hi, Maria. Thanks very much for your talk. It's very interesting, like research and work. I'm pretty sure there are lots of questions. So maybe I can start with one question that is on page 10 of your slides. And
I will share again then. Yeah.
So page 10.
Yeah.
Yes. So it's very interesting to see that the hands find an optimal scoop. But I'm wondering here, there is a object information from the environment, right? So the previous work in the information of object, maybe, for example, the grasp net, they use camera to capture the point cloud and analyze which direction is the best or optimal way. So I'm wondering, like, is there any difference? For example, do you also use camera or visual perception, or is there any other methods you get the object information?
Yeah, indeed. I mean, I skipped this part. I just said it quickly. We had a camera supervising the task, and actually the camera was needed to first. So the camera would take the point cloud of the object and of the environment and the object environment relative position. Then thanks to a network that we trained, we would choose the best scoop, because we had several different scoops for each hand. Okay, so here we see, okay, for example, for the pizza hand, we found 4 different scoops. So based on the object and the position of the object with respect to the constraint, we would choose the best scoop and then align it with the environment. Whereas in the baseline, we were just computing using a simple planning based on the center of the object, which again was computed by vision.
Understood. Yeah. Thanks very much.
The camera.
So, yeah, there is one question in the chat. So regarding soft robots influencing robot learning, I'm curious about your observation on robot manipulation, on manipulating its environment, making use of its environment to facilitate its gripper tasks. For example, a robot learns that it can pick up or grip an object by dragging it to the edge of the table.
Okay, no, let me just put it, okay. So the interplay between the robotic hand, so the hand design and the possible learning algorithm can be of various types, okay? For the moment, we only use the AI-based, machine learning-based frameworks to solve the perception part mainly. Then we would do the planning based on that. Now we are trying to actually solve more complex scenarios like cluttered environments, which can be tackled with, for example, reinforcement learning processes that allow to actually understand how is the scene and how to declutter a scene, for example. And we are trying to see whether having the scoop that separates objects directly while grasping them can simplify the network. So in that way, we don't have to learn 2 actions like separating and grasping, but just one. And we are trying to understand this thing. Indeed, another, I mean, there are works there in which, based on the scene, you can understand whether to grasp an object by using a certain strategies or another. But indeed, this is a nice direction to go and to explore more. Thank you.
Thanks very much. And another person asked, do you consider the hand in human handover task as a soft environment?
It's a sort of a soft environment indeed, where the human hand can be both soft and rigid depending on when we interact. So we didn't explicitly model the stiffness of the human hand, but indeed it's a mix, no? It's both soft and rigid.
Yes, true. Yeah. And a new question comes. So did you calculate the force required to grasp the object or slip estimation while holding the object? Because there is a chance of deformation of objects or damage to manipulator and effector.
Yes, sure. I mean, in these, in all these, mostly all the things I showed, there is always a force torque sensor at the end effector that allows to check whether the hand entered in contact with the object or with the human hand, and also in the slip task towards the edge, we were using force information to, and we were actually controlling the force performed by the hand on the object in order not to lose the object, nor to break the system. Yeah, indeed, there are force sensors at the end effector.
Thank you very much. And people are welcome to open your microphone to ask questions if you want. And maybe I can ask another question if there's time. So I think one of the main major issue to use softer materials in robot gripper is that we cannot control the actuators, right? So for example, if it's soft materials, we use tendons or cables to control, but that means we lost the degree of freedom of the, for example, a hand joints like this, right? So do you think that's like solvable in the future, or is there any clue about this kind of point?
I thank you for the question. Indeed, softness is very much related to under actuation. So every time we have a soft gripper, it is typically under actuated, either because there are tendons, like in the Pisaietti soft tendon, it's just one motor, and then the hand just closes and opens 19 degrees of freedom. Whereas when the hand is pneumatic, the degrees of freedom are potentially infinite because the deformation is continuous and there are just a few channels for inflating the hand. So indeed, under actuation is a huge part of the point of the soft hands. I'm not sure we want to really solve this problem because we created it. So indeed, if we want to do, I mean, this is a trend now that is going towards having soft hands with more degrees of freedom to have more in-hand manipulation capabilities, for example. So indeed, if we want to go towards in-hand manipulation, we need to enlarge the number of actuators. And still, the softness can play an important part because still it allows to account for small variations in the object positioning that might not be accounted for when you have a rigid hand. So even in soft hands with more actuators, still the softness is fundamental. But the whole thing of soft manipulation, at least at the beginning, was really to go to hands that are as simple as possible from the control point of view, but can do a lot of different things thanks to the interaction with the environment and with the object. So the actuation comes also from the interaction. So I don't know if...
Yeah, thank you for the nice presentation. I think I can ask one question if you allow.
Yes, we can hear you.
Yeah. So a very nice presentation. My name is Amir. I am assistant professor at Yuhe University in Abu Dhabi. So first of all, very nice presentation and the scale of work that was represented and shown. Just two questions I have. One is when you mentioned you have a force torque sensor mounted at the end of the gripper, what kind of control strategies was implemented, like impedance control or some other kind of control strategies that are typically used when we use the environmental constraint to manipulate the objects or even to maintain a constant force. So like I think I saw one question in the comment also, like while you like that's like the amount of force feedback is also there, like how much force you need to require to grip it. And then the next part of the question is there are few kind of grippers which are like kind of an enclosure, like complete like a balloon which can enclose the whole 3D shape. So what's your comment on that? Like, because let's say if you are picking an orange and if something can enclose the orange from every side, so using pneumatic means. So what is your comment on that?
Okay, thank you for your comments and for the questions. So regarding the first question, what kind of control strategies we are adopting? For example, in the first videos about the exploitation of the environment going towards the edge, we were using a hybrid force velocity controller, whereas in the human-robot interaction task, in the soft endover, we were using an impedance control to be sure not to damage the human and so on and so forth. And instead, about about the universal grippers are called some of them, or there are monolithic grippers that allow to completely enclose into balloons or structures of pneumatic actuators the objects. Indeed, these are nice grippers that usually allow to do to grasp a lot of different objects. Probably it's more difficult to use them in those strategies that we saw. So indeed, if an object can be grasped from the top and is free from other objects, you can use that gripper. if you need also, for example, to separate objects or you have narrow spaces, then it depends on the gripper capabilities, no? To whether it can really grasp it or it needs to find a good surface where to grip it. So in that case, maybe having a gripper that allows to exploit the environment might be needed. Thank you.
Yeah, thank you. Yeah.
I think there's another question in the chat. So is there a specific soft hand among the ones you presented you would suggest to integrate with reinforcement learning? As you mentioned, there is a gap to have better manipulation, depending on your perspective on how you see the advancement of soft hands for the future.
Okay. I don't have a complete answer to this because I mean there are so many different soft hands and so many different approaches in reinforcement learning that probably it really depends on what is the task you want to do. I can tell you what we are trying to do. We are trying to use the scoop gripper in decluttering because the scoop gripper is particularly suited for that task because it has this scoop that allows to separate object and so on. Probably it really depends on the task, and also I would say in general probably having less complex grippers featuring a few a small number of motors. I mean the Pizza IT soft hand has one, the scoop gripper has 3 or 5 depending on the implementation. Probably would be better not to overload, you know, the number of degrees of freedom you have to control for with respect to the hand. But yeah, I don't have a final answer to this question, and thank you. Actually, it's interesting.
Yes, it's always depends on the tasks, what kind of gripper you choose.
Yeah. I mean, now most of the implementations are done with two-fingered grippers, parallel grippers. Even if for handover, for example, we saw that typically there are two-fingered grippers that tend to avoid the interaction with the human. So the idea would be, let's start to use even more complex, from certain points of view, hands to see whether we can gain something else, let's say.
Yeah. Thanks. And another question is that could you explain again how to calculate the optimal objects grasping based on the shape and pose of the objects?
Okay, so this depends on the work. Usually, but most of the times, let's say we use the RGBD camera. We took the point cloud and we worked with the point cloud, either giving it, for example, in the first example where you saw the RBO hand, we were using the DexNet, the very first initial DexNet, and we fed it with the RGBD images. Otherwise, in the slight wedge thing, and also actually in the end in the handover part, we take the RGBD images and we extract from them the point cloud, and then from that we compute the bounding box, and then we align the hand. Usually we do this. Even for the scoop gripper, we did like that. So yeah, mostly this.
Yes, I think it's like very important to use point cloud in these kind of tasks. Otherwise, there's no information at all.
Yeah, but we typically, because since the hand is the one that ends the job, we usually only need to know where is the longest side and where is the center of the object. More or less, these are the information that we need. For the scoop gripper, in the very first paper, we also evaluated, we actually did something a little bit more, in the sense that we took the point cloud, we put it in simulation, we computed the best plan, the best pre-grasp pose according to a grasp quality index, and then we achieved that pre-grasp pose with the gripper position in a certain way with respect to the object, and then we let the gripper finish the grasp in the sense that we would then control the robotic arm to grasp the object. So yeah, different things, but yeah, typically RGBD input is enough.
Thank you very much. So is there any other questions?
Yeah, I might have a question actually. It's more a curiosity. I'm not an expert in manipulation myself, so it's more because I had the opportunity to talk with other people working on manipulation tasks, but from a totally different perspective, and they were studying the problem by using quality diversity algorithms to learn in simulation grasping and then have a better model and more robust system. I wonder what is the role of simulation in your work, and if you try also to fill this gap between simulation and reality, and if you have a learning part for the model-based part of the task that you mentioned. How do you build those models? Do you use some heuristics? Do you learn those models from before with simulation? And if not, are you planning to do so?
Okay, so with soft hands, bridging the gap between simulation and real world is very difficult. So we tend not to do it, sort of. I mean, there is a whole community that is working on simulating robots and soft hands. So if you want to have a precise control of the hand, clearly you need to know what happens when you actuate it. And so you have to know, you have to have learned or modeled a function that maps the actuation inputs to the actual final configuration of the hand. In the works I showed, we are not concerned completely about the final configuration of the hand, in the this don't want to plan exactly the final grasp. This is why in some of the works we simply align the hand based on a model of the hand. So we model how the hand closes. We see that there is a principal direction along which the hand closes, and this is independent from the type of hand. So this is the model, and we align the hand along the best direction on the object, which is however computed through a network, neural network. So the learning comes typically for the perception of the object. So we used, for example, DexNet that gives you the best grasp direction for a gripper, okay, for a parallel jaw gripper. I didn't go into the details of this, but so it gives you the best direction for a parallel jaw gripper, the center, and what we did was to just align our soft hand with the preferred direction of grasping of the soft hand with that direction. So, and then that's it. So what happens next is that the hand closes around the object, and this is left to the hand. The same applies for the scoop gripper. We optimize the pre-grasp pose, so we wanted to be sure to place the gripper in the right orientation with respect to the object, but then we would let the gripper go and grasp the object. And so of course, this problem comes when you want to learn something, because learning in real world is very complex. So in the work I was mentioning that is ongoing, we actually had to simulate the scoop gripper, while in the first papers we used a toolbox that we developed in Siena that is called SceneGrasp, and it mostly deals with quasi-static grasping. Now we also have something dynamic, but we use the quasi-static part. Then for this new part with the learning, we started using Coppilia Sim, so with also dynamic simulation, but we also performed the learning with real examples, really, because we wanted to be sure that we were modeling the gripper in the right way. Indeed, for example, for the scoop gripper, in the end, it's not that difficult to model because it's rigid parts connected to flexible parts. The problem of modeling comes with pneumatic hands or even hands that exploit very, very soft, continuous soft materials. When you stay with articulated soft hands, so-called, typically you can model them in a good way, let's say.
Yeah, I imagine like you really need a very good physics simulator if you want to. We have another question, I think. Yuhe, do you want to?
Yes.
Then we will close, huh?
Yes. So the last question is, could you comment about learning efficiency, especially grasping a dynamic object such as a flying ball?
Okay, we didn't do this kind of tasks. Indeed, these are interesting. There are groups that are developing these kind of strategies. Again, the problem with dynamic object grasping with soft hands can be that some of the prototypes are rather slow in closing. They're not very fast, like a parallel jaw gripper would be, or a rigid hand could be. So the object, the implementations that that are there since several years with the objects flying and the robot that grasp them typically have rigid hands, maybe a bit even tendon driven, but still quite fast in the closure. So that would be the main problem with the hands that we used so far. Indeed, again, it depends on the hardware and on the task. So yeah, I don't know. I couldn't say much about this because we didn't try.
Yeah, I think currently the soft hands is not so fast in response.
Exactly.
Yes, maybe there's some research in the future about dynamic objects.
No, indeed, there are a lot of different prototypes. So there are actuation types that allow, so like be still with things that allow to be very fast. But we didn't deal with those yet.
There's different research directions. Yeah, thanks very much. And I think currently we are like at the end of our talk. And thanks again, and very appreciate for your talk today. And it's very like insightful and very exciting talk, and which brings about the soft grippers and soft materials in robotic manipulation. Yeah. So I saw.
May I have one more question? Hi,
Yeah.
we just did not run out of the time, I'm sorry. So this is Miklos. Hi, Maria. Thank you for your talk and congratulations for all of your results. I was just wondering that I know that it's this similar question multiple times already arise, but do you see any chance that how can you make more theoretical the design step of the compliant behavior and the material, the elastic properties of the materials you are using? How can it be so how can you not just empirically find out what kind of material to use and empirically try it, but involve more precisely in the design steps that what kind of parameters exactly to apply in the case of different grippers, for example?
Okay, thank you for the question. This is more related to the way you design, right, the hands. So the work I presented is more like sort of a data-driven design, in the sense that we did a lot of grasps in simulation to then design the optimal scoops. This is done model-based anyway, up to a certain point, and then we use clustering algorithms to cluster the prototypes. So it's a more data-driven, simulation-based design. Regarding more accurate simulation of the materials, what I can tell you, we for example, colleagues of mine worked on defining the optimal in-field density of the flexible joints of the fingers to actually get a certain stiffness and does a certain closing trajectory of the finger, for example. What we did in terms of simulation was, for example, to start from complex. I mean, this work is a 2018 work. We did basically we started again from very complex FEM simulation of a very soft finger like the one of the RBO hand, so a continuum robot, pneumatic actuated robot. Then from those we extracted the parameters of a lumped model, okay, so assuming the finger as a lumped parameter model as a kinematic chain with the revolute joints and rigid, very small rigid links. And then based on that, we were simulating the hand in a simulator, in a dynamic simulator. So we started from very complex data, and then we tried to go and reduce the number of important parameters, and in that case was the stiffness in the 3 directions, in the 3 rotational directions at each of these discretized joints. So again, here maybe one can think of using this kind of approach, or even use FEM simulation, and then based on that optimize, I don't know, the material properties or other problems. The main problem is to really find the good material model to use. Okay, so the problem is that because it's very highly deformable material, so sometimes the elastic assumption doesn't hold for these robots, for the pneumatic ones in particular. I don't know if I answered your question. I mean, I answered
yeah.
my experience.
Yes.
But
thank you very much.
Thank you
very much.
Thank you all. And I think now is at the end of our talk. And thanks again to Maria to join and give us a talk. Thanks very much.
Thank you. Thank you so much for inviting me, and thank you all for the nice discussion.
Thank you. Thank you, really. It was really interesting.
Bye-bye.
Bye.